All right, we're going to start this video by looking at what's called 2D orthogonal projections. So if we're given two vectors, v and w, we want to find cw and z, where cw is a scalar multiple of the vector w, and z is a vector that's perpendicular to w. And so it's also perpendicular to the cw vector, the scalar multiple of w. So cw plus z, as you can see in this picture, is equal to the vector v, right? So you can think about this vector v as being decomposed into two pieces, two vectors. One that's a scalar multiple of w, and one that's a vector that's perpendicular to w. Now, why would we want to do that? Well, this will foreshadow what we'll do a little later, but one reason is if you're restricted to stay on the line formed by the vector w, well, the closest you can get to the vector v is cw, right? And that smallest distance is the length of z, right? So the closest you can get to v by staying on w is the vector cw, and the distance between cw and v is the length of z, right? That perpendicular distance. All right, so that's a little foreshadowing. We'll see that more come up later. But first, we just need to figure out what these vectors c, w, and z are. The way to calculate those vectors is by noticing that z dotted with w is 0, right? Because z is orthogonal to w. And we can substitute what z is, right? Since cw plus z is v, you can rearrange that to have v minus cw being equal to z. So we substitute v minus cw in for z. And then we know with dot products, you can distribute that w to both the v and the cw. So now v dot w minus cw dotted with w is equal to 0. So that's the distribution property. And then you can solve for c, right? Rearrange the equation and solve for c. You get v dot w divided by w dot w, right? So that scalar multiple of c is the ratio of those two dot products. Right? Each dot product is a number, so you'll get a number divided by a number. That will be your scalar multiple of c. And if you know your scalar multiple c, then we know what cw is, right? Because w is given. So cw is v dot w divided by w dot w, all multiplied by w. Right? So that fraction is just a number being multiplied by w. We're scaling w. And then we can find z by just doing v minus that result of cw. Right? V minus v dot w divided by w dot w times w. Right? That's just rearranging the addition of the two blue vectors, cw plus z, equaling v. Right? It's solving for z there. Right? V minus that cw vector. This would be a great spot to pause the video and just re-look at all the math that was happening and look at the diagram and make sure it really makes sense on where this calculation came from. And these two calculations of our constant multiple c and figuring out what cw and z are really important, and we'll rely on this math for the rest of this video. So this would be a great stop to stop the video and see if it all makes sense, and if it doesn't, definitely ask me questions. All right, we're going to look at how to find a 3D orthogonal projection. So this time we're going to be given three vectors, a vector v, and a vector w1, and a vector w2. And here we're going to have w1 and w2 be orthogonal. So that'll be a requirement for this projection. All right. So here's a picture of w1, w2, and the vector v. And what we're going to try to do is find a linear combination of w1, w2. Right? So c1, w1 plus c2, w2. That's a linear combination of those two vectors. So there'll be some vector in the plane spanned by w1 and w2. So it's in the same plane. And we're trying to get as close to v as we can while we're staying in that plane. All right, so we'll have this other vector that we can call z again that's perpendicular to that plane. And so like the distance between v and that closest spot in the plane is the length of z. All right, so in summary, we're trying to find that linear combination, C1W1 plus C2W2, where C1 and C2 are scalar multiples, W1 and W2 are the vectors, and we're trying to find that perpendicular vector Z. And note that the sum of those will equal the vector V. So that linear combination plus Z will get you to the vector V. All right, there's another way we can think about what we just did, and this is what we're going to focus on for the rest of the video, and then later we'll get back to this closeness idea. What we've done here is we also produced a vector Z that's orthogonal to W1 and W2. So now if you take the whole collection of W1, W2, and Z, right, those are three vectors that are all orthogonal to each other. So you have this orthogonal set of vectors. The dot products between each pair of vectors are 0. Sometimes we'll start with vectors that are not orthogonal to each other, and we can use this process that we just did to get an orthogonal set by working with the vectors that we were given. The initial vectors might not be orthogonal, but we can do this process to produce orthogonal vectors that give us the same span, right, as our original vectors. All right, so this process of producing an orthogonal vector, orthogonal to the other vectors given, to produce an orthogonal set of vectors where all the dot products between each pair of vectors is 0, we can generalize this to any amount of vectors, and this is the Gram-Schmidt process. All right, so if we're given a set of vectors that form a basis for inner product space V, so inner product space is just a vector space that you have an inner product defined on. Remember, inner product is just a function that assigns a number to a pair of vectors. So if you have some basis for that vector space that also has inner product for it, associated with it, then we can produce an orthogonal basis for that inner product space. And we'll denote that by B prime, right? That'll be the set, and the orthogonal vectors will be W1, W2, all the way to Wn. So let's just look at what's written here and kind of soak it in, right? Notice the requirements. The original vectors, V1, V2, all the way to Vn, right? We're looking at any amount of vectors. Those have to be basis vectors, so that means they're linearly independent and they span the inner product space. And they span the vector space that has an inner product associated with it. So they have to be basis vectors. You can't have like redundant vectors in there. So forming a linearly dependent set. You need a linearly independent set. So that's a basis. And also V1, V2, all the way to Vn, they don't have to be orthogonal. We're going to produce an orthogonal set of vectors that is also a basis for V by this process we'll describe here. So first, you can let the first vector W1 just be V1. So that's the first step, nice and easy. Next, the second vector W2 is going to be V2 minus the ratio of the inner product times W1. Notice this is the exact same calculation we did a few minutes ago, but we're using dot products instead of inner products because our vector space was R2 and R3 for those last two examples, and we're using dot product as our inner product, so that was our inner product space before. So the exact same calculation, but now it's more general, just using a general inner product that we can choose different inner products later on. But it's the exact same calculation that we solved for Z before. Right, that was the same calculation in the R2 case. To get the third vector, right, this was the same exact calculation that we did for the R3 case. We find the 3D orthogonal projection. Now we're just using inner products instead of dot products. So we want to generalize it so you don't have to use the particular inner product of a dot product. But you can keep doing this pattern all the way to the nth orthogonal vector would be this calculation. So you could just about to pause it and just notice the pattern that's happening. And really, just really notice it's the same calculations that we did with the dot products a few minutes ago. So the moral of the story is here, if you start with n vectors that aren't orthogonal, you can produce an orthogonal set that spans the same space using this process. And this process is a series of calculations. They're exact calculations we just looked at when we're looking at R2 and R3 with dot products. Now it's just generalized to any vector space, really inner product space, where you get to define an inner product that you'd like to work with. All right, let's implement this Gram-Schmidt process to these three vectors. These three vectors form a basis for R3, meaning they're linearly independent and they span R3. And this process of producing an orthogonal set is called orthogonalization. Right? So if B is that original set that's not orthogonal, then B prime, which we'll call the set of three vectors W1, W2, and W3, that is an orthogonal basis of R3, where, and the first step of Gram-Schmidt process is let W1 be V1. Right? So nice and easy. There's our first vector for our orthogonal basis. It's just 1, 1, 0. It's V1. Now W2 is V2 minus that ratio of dot products that we derived earlier in the video, and we multiply that by W1. So that's step 2 of the Gram-Schmidt process, and we can calculate that ratio of dot products to be 3/2, and then performing the subtraction in that scalar multiplication, we get the resulting vector -1/2, 1/2, and 0. You can double check that W1, W2 are orthogonal. Right? You'd get -1/2 plus 1/2 plus 0 is equal to 0. So dot product is 0. Those two vectors are orthogonal. Now we still need our third vector, W3, and our formula for that from the Gram-Schmidt process that we derived is V3 minus the ratio of dot products times W1 minus the other ratio of dot products times W2. So those ratios shown there. And we can compute those ratios of dot products. The first one is 1/2, and the second one is 1/2 divided by 1/2. All right. And performing that subtraction scalar multiplication, you get the vector 0, 0, 2. And you can check that vector is orthogonal to both W1 and W2. And so we have created an orthogonal set of vectors that form a basis for R3. We formed it out of this original set of three vectors, V1, V2, and V3. Now I can go one step further and do an orthonormalization. Right? That just means orthogonalization and then normalize the vectors. So far we have this orthogonal basis that we just computed using the Gram-Schmidt process. Go one step further and find the unit vector in the same directions as all of these vectors W1, W2, and W3. So we'll call that U1, and we know how to find the unit vector from before. That's W1 divided by the length of W1. And there's that vector, 1 divided by square root of 2, 1 divided by square root of 2, and 0. So that's a vector that is length 1 in the same direction as W1. All right, we do the same thing for W2. Get a new vector U2 that is a unit vector in the same direction as W2. And same thing for W3. We get U3 in the same direction as W3, but has length 1. And that's an orthonormal basis, meaning they're orthogonal. Right? Their dot products are 0, and they all have length 1. So we call that an orthonormal basis for our vector space R3. Let's look at another example. So let V be the column space of this matrix A. So this is a 3x2 matrix. Remember what the column space means. It means the set of all linear combinations of the columns of A. So you can treat each column here, the two columns, as a vector about all linear combinations of those two vectors. That give you a plane in 3D space. Right? So the set B being V1 and V2 would be 0, 1, 0 and 1, 1, 1. That would be a basis for V. Right? The two columns of A form a basis for the column space of A. Now these columns are not orthogonal, right? So we're going to try to create an orthogonal set, an orthogonal basis for the column space of A. All right, so B prime would be W1, W2 again. And that's the notation we're using, W1, W2. are going to be the orthogonal vectors. It'll be orthogonal basis of V, where, remember the first step of Gram-Schmidt process is let W1 be V1. So there's our first vector in this new basis. And W2 is V2 minus the ratio of dot products there times W1. Right, that's the ratio of dot products we developed at the beginning of the video. And that ratio of dot products is actually just 1 divided by 1. And so performing that subtraction of vectors, you get the vector 1, 0, 1. And check it out, W1, W2 are orthogonal to each other. And you can normalize this orthogonal set of vectors, meaning turn these vectors into vectors that have the same direction but length of 1. So that'd be the orthonormalization part. And you'd get this new set of two vectors. These would be orthonormal vectors that would form an orthonormal basis for our column space of the matrix. So right now we're just showing the process of the Gram-Schmidt process. In the next video, for the next homework, we'll see how to use the Gram-Schmidt process to solve pretty interesting problems. But we're just going to focus on the process right now and get into applications next time. All right, one last interesting example would be considering the vector space P2. Remember, P2 is the set of all polynomials of degree 2. And the basis for P2, one particular basis, would be 1x and x squared. Right? Think about all linear combinations of 1x and x squared. You'd get all polynomials of degree 2. And we'll use the inner product. The inner product of f and g is the integral of f times g dx from -1 to 1. Right? We showed before that this satisfies the 4 properties of an inner product. And eventually, in the next video, we'll see that having an orthogonal set of functions for P2 would be really nice. Right now, this set 1x and x squared is not orthogonal. You can double check. Say, for example, find the inner product between 1 and x squared. Well, that'd be the integral of x squared from -1 to 1. That's not 0, so it's not orthogonal. And so the Gram-Schmidt process will give us an orthogonal set of functions in P2. All right, so let B be this non-orthogonal set, then B prime will be this orthogonal set that we've been calling W1, W2, and W3. Be an orthogonal basis of V, where, remember the first step is let W1 be V1. In this case, V1 is just the function 1. So we're just going to let W1 be the function 1, right? The constant function 1. W2, given by the Gram-Schmidt process, is V2 minus the ratio of inner products times W1. Right? And if you compute that ratio of inner products, right, which are the integrals in this case, from -1 to 1, you'd get 0 divided by 1. So really, you just have x minus 0, and so W2 is just the function x. So apparently 1 and x were already orthogonal to each other, so the Gram-Schmidt process just gave us V2 back as W2. Okay? And you can double check. Right? If you find the inner product between W1 and W2, that is 1 and x, that'd be the integral from -1 to 1 of x dx, and that is definitely 0. So you can verify that. All right, in W3, right, from the Gram-Schmidt process, you have to compute V3 minus the ratio of inner products times W1 minus the other ratio of inner products times W2. So those inner products are integrals. And you can compute those integrals and get 2/3 divided by 2 for that first ratio and 0 divided by 2/3 for that second ratio. And therefore, x squared minus 1/3 is W3. So that's our third orthogonal function for this orthogonal set that forms a basis for V. And you can go one step further if you'd like and find the orthonormal basis, which would be normalizing each vector W1, W2, and W3, right? By computing the norm of each one and taking the vector and dividing by its norm, right? And the norm, you'd have to use this integral to calculate the norm, but I'll let you do that on your own if you'd like to find the orthonormal basis. All right, so this Gram-Schmidt process will be really important. In the next video, we'll be able to do some pretty neat things with an orthonormal or even just an orthogonal basis for a vector space. All right, that's it for this video. Thank you.